Okay, scalars and vectors. At some point in these videos, there are going to be chances for you to pause and to answer questions. When you do pause and start writing down, later on the answers will come up, so you'll be able to mark them. Any questions or any concerns for things that you got incorrect, you can either record or rewind the video or come and ask us for some help at school. So, scalars and vectors, this is super common. Some questions about these come up all the time. So make sure that you know the difference between a scalar and a vector. But what does it actually mean? We can sort things into categories, and anything that we can measure, anything that we can put a unit on, we can put them into two groups as well. We can either put them into the scalar or the vector group. Scalars are things that we measure that have a magnitude only. Now, magnitude just means a size. So if I wanted to measure the height of Mr. Vector here, he would be, let's say 5'4" tall. That is a magnitude because it has a size. Vectors are things that we measure that have magnitude, size, a number, and a direction. If Mr. Vector was flying through the air, the direction that he was going in would just by itself, by itself, the direction that he was going in would be depended on how he was lifting off, which direction he was pointing, what forces are pushing him. And if we know that he was going 3 meters per second as he was going in that direction, then we could call the combination of these two things, the direction he's going in and the speed that he's going in, a vector, because it has a magnitude, a size, and a direction. The direction is really important. If we're talking about momentum, and if we're looking at the crash between two objects, whether they're going towards each other or away from each other is really important. Not only will it determine how much damage is caused, but it will also affect the maths that we use as well. Here's some examples of scalars and vectors. Now, some of these are paired. Direction and displacement. If you're going from point A to point B, and you don't go in the same direction, if you take a wandering around route, then we call that a direction. If you're going from A to B, and you're just going in one straight line without changing your direction, we call that a displacement. If you traveled at a constant speed of 3 meters per second while doing this little route, A to B, and your direction was changing all the time, we call that a speed. If you're traveling at 3 meters per second and you never once change your direction for the time that you're going that speed, we actually call that a velocity because it has a direction. Mass, measured in kilograms, is the amount of stuff in a thing, the amount of mass. You can also talk about inertial mass. Spelled that wrong. Which means how difficult it is to move something. Now, mass doesn't change. So here's Earth, here's the Moon. If something here is 1 kilogram on Earth, it will also be 1 kilogram on the Moon. Forces, including weight, are vectors because they act in a direction. Weight is mass times gravity. So if I've got 1 kilogram of something on Earth, it would have a weight of 10 newtons. However, because there's less gravity on the Moon, something like 2.2 is the value for G on the Moon, it would only have a weight of 2 newtons. Have less weight, even though it's still a kilogram, it would have less weight. Temperature in degrees Celsius and energy measured in joules are two more scalar options. And because acceleration is the change in velocity divided by the time, notice that it's velocity, not speed, we call acceleration a vector as well. And momentum. The equation for that momentum is mass times velocity. These are those definitions for distance and displacement for you to pause and look at. And now here are some questions for you to pause and try. Here are your answers. Here are some definitions for speed and velocity for you to pause and look at. And here's an example for some speed calculations. Now, I'm going to go through this one in detail and show you exactly how we want you to set it out. So you can pause and look at it if you want to. We're going to read through the question. A bike travels 800 meters. I'm going to write down my number, 800 meters. I know that m is the symbol for meters, and that distance is the symbol equation for meters. Pardon me, d is the symbol equation for distance. In 160 seconds. 160 s. I know that s is the unit for time. Calculate the average speed of the bike. Speed is equal to, I don't know how many meters per second. Find the equation from my list of equations. Distance equals speed times time. And now you can either put your numbers in first and then rearrange, or rearrange and then put your numbers in. It's up to you. I'm going to rearrange first, because I'm a rebel like that. Speed is equal to 800 divided by 160, giving me an answer of, I can't do that in my head, though I should be able to, 10 over 2, 5. Hey, 5. Just wanted to double check because it's being recorded. And I'm adding my units in. Now, while this is correct, we must always use this method of doing our maths for the exam technique. Here's another example. See if you can do it yourself. Pause. And here's your answer. Here are some velocity calculations. Remember that it's the exact same thing. If speed is equal to distance divided by time, velocity is displacement divided by time. Remember, displacement is the straight line distance between A to B. Speed is a scalar, B is a vector. Try the questions. And here are your answers. Now, at some point, we're going to be looking at distance time graphs and velocity time graphs. So a couple of definitions so we know what we're talking about. Average speed is the speed of an object over the entire journey. We're going from A to B. And just pretend that this is a straight line, because I'm annotating with a mouse, so bear with me. It's a straight line. And you traveled from here to here at 2 meters per second, and then from there to there 4 meters per second, and then from there to there 1 meter per second. You stayed here for a little while, and then you raced to the finish line at 7 meters per second. All these different speeds, in fact in this case, because it's a straight line, all these different velocities can be found by finding the total distance traveled over the total time taken. If I wanted to find the average speed, I do the total distance divided by the total time. If you're asked how to measure that, you can use tape to measure the total distance, or a trundle wheel if it's a long distance. And to measure total time taken is a stopwatch. But it's probably a better idea to use a data logger or a computer to time it to reduce the impact of a reaction time. So average speed is the total distance divided by the total time. It gives you the mean speed that you're moving. Instantaneous speed, however, is a snapshot. So if I was to look just there, my instantaneous speed would be 2 meters per second. The speedometer in the car gives your instantaneous speed. Distance time graphs can represent the motion of an object for a certain amount of time. There are 2 different types of graphs, distance time graphs and velocity time graphs. We'll be looking at both. Gradient is the slope of the line. How steep is the line? And different gradients show different motions on the object. Now these gradients mean different things if you have a distance time graph or a velocity time graph. In a distance time graph, if you have a steeper slope, then you are going faster at a steady speed. If you have a less steep slope, You are going at a steady speed, and you are going less fast than the steeper slope. If you look here, my object has gone a certain distance. Let's just say this is 2 meters. And it's after 3 seconds at this point that I'm circling. My object is at 2 meters. My time is continuing. 3 seconds, 4 seconds, 5 seconds, 6 seconds, 7 seconds. For those 7 seconds, the object has not increased its distance. And that means it's stationary. It's traveling at 0 meters per second. If we see a negative gradient, it just means that I had an object here, started off at steady speed, stayed there for a while, and then came back. This is what it means by returning to start. I'm going to get rid of my scribblings, and you can have a little look at that picture and pause. How can we calculate speed from a distance time graph? You can see here that the steeper the gradient, the faster the object is traveling. The gradient in the line of the distance time graph is the speed of the object. What does that mean? The gradient, to calculate the gradient, we just do difference in y divided by the difference in x. So let's look at an example. Work out the speed of the object shown on the red and green line. I'm going to do the red line. So what's the difference in y? Well, my red line got to 50 kilometers. And it started at 0 kilometers. Difference in x. Finished at 5 hours and began at 0 hours. So I can now find my gradient. Notice that this is a distance and that this is a time. So if I want to find my speed, I do my distance, 50, divided by 5 equals 10. We don't know why that says 30. Well, I found the average speed, and I think this is just finding instantaneous. Oh, well, that's what it is. Choose any points in these lines. Forgot to mention. You can choose any of the points in any of these lines to find the speed. The only time you'd have to find a different gradient is if the gradient of the line changed. See? Well, this is interesting. It's entirely useless. So I'll get rid of my scribblings again. You can have a go of that if you want to. You can pause it. Mind you, the working out is shown there. There'll be more opportunities for that later. Acceleration is the change in velocity divided by time taken. V stands for the end speed. U stands for the start speed. When objects accelerate, they're changing their speed or changing velocity. Or we can say that they're changing direction as well. Acceleration is the rate of change in velocity, and because velocity is a vector, so is acceleration, as we've already said. Here's an example. A car accelerates from rest, and this is important because when you see rest, you've got to think 0 meters per second, to 30 meters per second, 17 seconds. So the end velocity in this particular instance was 30 meters per second. Start velocity was 0 meters per second. The time taken was 17 seconds. My equation, A is equal to delta V divided by T, V minus U. 30 take away 0 is 30, divided by time. Give me my answer, 1.76 meters per second squared. This squared does not mean that you have to square that number. If you're given an equation like this, with acceleration in it, and acceleration is 2, meters per second squared. That does not equal, no, 4 units of acceleration. ACCL there just for acceleration. The meters per second squared is referring to the unit. 2 squared meters per second is equal to 4 units of speed or velocity. Again, I'll take away my scribblings and you can have a look at that. Acceleration is a vector, so the direction of acceleration is important. When a moving object has a negative acceleration, minus 2 meters per second squared, for example, it can either be slowing down, called decelerating, or it could be increasing speed in the opposite direction. An acceleration of 2 meters per second squared in this direction. If it's going in this direction, I could call it negative 2 meters per second squared. If the car is moving along a straight motorway at 70 miles per hour and then has a negative acceleration, the car will be slowing down. But if the positive direction is chosen to be upwards when a ball is dropped, so my ball is here, let's say that positive direction goes that way, it will have a negative acceleration because it's accelerating towards the ground. Negative is in this direction. We'll continue accelerating in that direction at 9.8 meters per second squared. That's an 8, by the way, 9.8 that's supposed to say, because of the force of gravity. The acceleration due to gravity. This is an equation that you might be given. I actually tell you what I'll do. I'll just get rid of my scribblings and I'll leave that there as well for if you want to have a read of that. This is another equation that you get given, and it means the same thing. We've seen all these symbols before. V is your end speed or end velocity, U, start velocity, A, acceleration, X, distance. Notice here that it's V squared and U squared. So it would look like this, 2 meters per second squared, squared. Now that would be the same as 4 units of acceleration, because we're squaring the velocity. Oh, silly biddies. There is no second square. That I was trying to do the exact opposite of what I just did. If it was 2 meters per second squared, that is equal to 4 meters per second. It's not saying 2 meters per second squared of acceleration. Okay, sorry, it's difficult just talking to oneself, talking in front of a computer. I did exactly the thing that I didn't want to do. This is V squared, not A squared. So it's 2 meters per second squared, which is 4 meters per second. We're not squaring the unit. We're squaring the number. Dope. Count the mistakes. The person who counts the most mistakes gets a special prize. Here's your answer. Try it yourself again. You can have a look through that. And there's your answer. Now we saw distance time graphs. This is velocity time graphs. It's because we have velocity now on the y-axis. It's more information than a distance time graph. It gives speed, distance traveled, time, and acceleration of the object. It will look the same. The axes are different. Velocity is on the y-axis. And here's what they all mean. Gradient in a velocity time graph, shows the acceleration of an object. Look here. This steady speed started at 20 seconds and finished at 40 seconds. For that chunk of time, from 20 to 40, this object was traveling at 20 meters per second. The speed has not changed. If we see a decreasing line, that's deceleration. You probably won't see this, but if there is a swoopy line, a non-linear line in this graph, then a non-linear trend, pardon me, it means increasing acceleration. So the acceleration isn't constant, it's changing over time. So we can find the velocity of an object at any point by reading off the axis of the graph. So at this point here, this object is traveling. I'm going to choose a better bit if you don't mind, just so you can see my dots. So this one here, the velocity of my object at that particular time is 15 meters per second. So at 7 seconds, this object is traveling at 15 meters per second. Acceleration is found from the gradient of the line. Now remember, the gradient is the difference in y divided by the difference in x. I'm not too sure why this line keeps appearing. Maybe it's a little ghost in the machine. So let's find the difference in y here. For section A, the object was going at 20 meters per second after 10 seconds of time. It started off at 0 meters per second. Delta y, 20 meters per second minus 0 meters per second, equal to 20 meters per second. Delta x, change in the x-axis, which is time, ended up at 10 meters per second. Take away the start, 0 minus s, 0 meters per second. And that's supposed to be seconds. 10 seconds. Honestly, I can do this stuff. I think it's just when you're sitting here talking to yourself, you go a bit mad. Then we do delta y divided by delta x. 20 over 10, 2 meters per second squared. To find the gradient, it's the change in y over the change in x. Now, remember this though, right? Or just so you know, delta y over delta x is the same as the change in velocity. So this was 20, this is 0, this is in velocity. So the change in velocity was 20 meters per second, divided by the time taken. The change in x is the time taken. There's 10, there's 0. The difference between those is 10 seconds. Now, if I want to find the distance traveled, I just have to find the area under the line. I don't need to know why, I just need to know how to do it. So this is my line. I need to find the area of this section. To do that, I'm going to use 1/2 the base times the height, because it's a triangle. I can find the area of this, 1/2 the base times the height, because it's a triangle. The shape here. And for this, I'm going to do the base multiplied by the height to give me my area of this boxy shape. Base here is 10, base here is 5, and the base here is 15. The height for this is 20, the height for this is 20, the height for that is 20 also. So, just got there are my numbers that I'm going to use to find the distance traveled. So, looking at how to describe the motion shown in a velocity time graph. Here's how I would say it. From 0 to 10 seconds, there's a constant rate of acceleration at 2 meters per second squared. We work that out by doing difference in y divided by difference in x. 10 to 15, I would say velocity here, personally. But at this point here, b is staying at 20 meters per second for the time between 10 and 15 seconds. So it's going at constant speed at 20 meters per second. Because my acceleration is decreasing, either going in a different direction or slowing down, difference in y divided by the difference in x will be given a negative number, negative acceleration, deceleration. Constant rate of deceleration of 1.33 meters per second squared, or minus 1.33 meters per second squared. And it turns out, when we find the area of all these shapes, that total distance under the line is 350 meters. To investigate motion. Oh, sorry, again, if you want to just have a read of that, by all means do so. Hopefully you will have done these investigations. If not, let myself, Mr. Patrick, and Miss Calvert know, and we'll do them with you after school. But we can investigate motion using a trolley or ramp and some ways of measuring time, speed, or distance traveled. So stopwatch, obviously, measures time. And light gates measure the amount of time it takes for something to pass through the light gate. Ticker timer, we have them, we don't use them. I'll make a separate video on what they are, because now that I've said we don't need to know it, I guarantee they're coming up in the GCSE. I do not guarantee. But the links for these two videos are going to be up on underneath my YouTube video. It's going to be uploaded soon, so you can have a look at it then. Now, these are some things that you need to memorize. No other way apart from just memorizing it. Make yourself some flashcards and just know them. Because they could ask you in a maths question, if someone is walking for 2 seconds, how far do you estimate them walking? So you have to know that the typical walking speed is 1.5 meters per second. So if they walk for 2 seconds, then they should have walked 3 meters. Terminal velocity then. If I have an object that's falling downwards, it's being pulled down by gravity. It's also going to be acted on by air resistance. When these two forces are balanced, then the object is still falling, but it is not accelerating, traveling at a steady speed. When it's traveling at that steady speed in a straight line direction, we call it terminal velocity. Terminal just means end. You can't go any faster than your terminal velocity. And the forces balance out. There's no increase in acceleration from the object, and that's that. That's the object. That's the speed that you go. Fun fact: there is no distance that you could throw a squirrel from that it wouldn't survive. Squirrels can survive falling onto the floor at their terminal velocity. So you could throw a squirrel from outer space onto the Earth, and it would be absolutely fine. Well, it would die, but only because of starvation. So don't do that. But you could if you wanted to, but don't. Acceleration in free fall is 10 meters per second squared. And there it is. So during the course of a skydive, the weight of the skydiver will not change, weight acting downwards. Say this person is 80 kilograms, we're going to give them a weight of 800 newtons. It's caused by gravitational attraction of the Earth. There will also be air resistance acting in the opposite direction. And that might not be balanced at the start. Maybe it's only 100 newtons at the start, but eventually you will get to the point where the forces are balanced. Which means their acceleration slowly decreases as they fall towards the Earth. They'll go from accelerating at 10 meters per second squared to 0 meters per second squared. And then hopefully a safe landing with 0 meters per second squared of acceleration too, though I suppose that would also happen if it wasn't a safe landing. When we hit terminal velocity, the weight and the drag are equal. Here are some estimations of everyday accelerations. I'm not entirely sure you need to know that, but it's good to know just in case you are doing questions. So let's say you're asked about the acceleration of a car. You come up with 29.4 meters per second squared. That's probably wrong. Very unlikely that we're going to find a family car that's able to accelerate at the rate of the space shuttle. Though it is interesting that a family car accelerates slower than a cheetah and a gazelle. So here's some questions. Pause as they show up. Then pause. Again pause. Again pause. Again pause. Hopefully you know what to do by now. If you don't, I failed you as a teacher. Or maybe you failed me as a student. And here are the answers. None of you have failed me as students. Don't you worry. Just talking to myself in my office. Well, it's a cupboard raining. You know, if you've gotten this far in the video, well done. If you haven't got this far in the video, why not? Well, you'll never know that I've asked you that question. I'm expecting you to pause at all these answers still, even though I'm not saying it. Golly, this has been exciting. And there's more! So, one of the things that you'll be asked to do when you're doing these, when we're looking at forces in motion, one of the things you could be asked to do is talk about this idea of stopping distance. So there's a little bit of biology going on here. It's good to know that a typical person's reaction time varies from 0.2 to 0.9 seconds. There's a number of things that affect your reacting time and in turn thinking distance. Now thinking distance, I'm sure it'll be explained later on. Let us say that you were traveling in an automobile and you spot a hazard there. Your car is going to keep on traveling for a little while before it can come to a complete stop. The distance that your car travels, while you're saying to yourself, oh goodness me, there's a hazard, I better start pressing the brakes. So the distance that the car is traveling before you press the brakes, the reaction time, is called a thinking distance. So you press the brakes at the X point, and it still takes some time for those brakes to work. Brakes don't just stop a car immediately. It takes a bit of distance. We call this the braking distance. Now, things that can affect the thinking distance, your reaction times, alcohol, caffeine, tiredness, and distractions. Now, alcohol increases reaction time, so it decreases reaction speed. Caffeine decreases reaction time, so it increases your reaction speed. Tiredness increases your reaction time, so it decreases reaction speed. And distractions, things like texting, which is a bugbear for me, nobody ever do it, decreases reaction speed because it increases reaction time. Drugs can either increase or decrease reaction times, as some drugs are stimulants and some are depressants. Caffeine is a stimulant, and alcohol is a depressant. Reaction times are so difficult. Like we said, about 0.2 to 0.9 seconds. Trying to measure it is difficult. Online tests are good. Displays a stimulus and measure the time that it takes for you to react to that, often by the clicking of a mouse button. Really far more accurate than a ruler drop. So you have a student's hand. Okay, this is a hand. Oh my God. That actually looks a bit like a hand. Oh my word, right. Well, this is so exciting. This is a hand. Like every good scientist, I shall label it. And a ruler is left hovering above it. When the ruler drops, it will pass through the hand. And depending on where the ruler is caught, you'll be able to figure out the reaction time. So if the student catches the ruler at this point, after it's fallen down, very quick reactions. If it's a point further up, they're going to have slower reactions. Now, you can find that website link underneath my YouTube video too. Here are the definitions for thinking distance, braking distance, and stopping distance we talked about earlier, except I might not have said specifically that this total distance here, from when you start thinking about stopping the car to actually stopping the car, that's stopping distance. But I'll put the definitions up here for you. Have a pause and have a read. This is an incredibly interesting graphic for those of us who are on the road. This gives us a stopping distance for cars at various speeds. So your thinking distance, the amount of distance you travel before you even think about pressing the brake. If you're traveling at 40 miles per hour, the highway code says that you can travel 12 meters before you even start pressing the brake. And it can take you 36 meters in total to stop and up to 24 meters for your brakes to work in your car. This is why you should always be hyper vigilant when you're crossing roads, because even if people are going at 9 miles an hour, it can take the length of 4.5 people lying on top of each other before the car even starts to stop, before the person can even move their foot to the brake pedal and start the car slowing down. Just have to be careful. Now, as you increase your speed from 30 miles an hour to 70 miles an hour, we can see that the stopping distance increases too. Those of you who don't know, this is the speed, normal urban speed limit, and this is a highway, so a motorway speed limit. Have a second to read of this, just what I said, but with better words. Okay, braking distance then. So you see the hazard, then you start to think about pressing the brakes. It takes a while for the message to get sent along your neurons before you start pressing the brake. And then when you start pressing the brake, which is our braking distance, combine the two of them, stopping distance. Looking at this now. Different things will affect braking distance. If you increase speed, you increase the braking distance, as we saw on those diagrams. It seems a bit counterintuitive, but bigger vehicles will actually take longer to brake, because the larger the mass, the larger the momentum, the larger the amount of force necessary to stop that machine. Now, there have been incredible advances made to brakes, especially in the big wagons, the big lorries, but still, as a rule of thumb, we say that to increase the weight of the vehicle, you increase the braking distance. Icy roads can lead to reduced friction between the tire and the road. Less friction means less braking, means a greater braking distance. Wet roads, the distance increases due to reduced friction between tire and road. That's the exact same thing as what was said up there. I don't know why I said it in a different term. I think it's possibly because it's been 39 minutes and I'm boring myself. Poor brake condition. So the way brakes work, you have your wheel, and around that wheel there's a little metal disc. And if you can just imagine like a clamp going on to that metal disc on either side, and the clamp squeezes in from both sides. So it squeezes in from the left and the right hand side. So you can see the left hand side, the right hand side is behind, the clamp squeezes in. If your brake pads don't work, or if that clamp doesn't work, if your brakes don't work well, then your braking distance will increase. And if you have bald tires, there will be a massively huge braking increase when wet, because there's actually, when you've got balder tires, there's less friction. So when you've got tire on a wet road, if you've got bald tires, that means that they don't have any of the lumps and bumps that normal tires have. And you put this bald tire on roads, then water acts as a lubricant, gets in between the tires, and can cause you to skid. It's called hydroplaning. This is a really bad drawing of a tire, but have a look at a tire the next time you're passing by a car, and you'll see that there are lots of bumps and grumps. And that's so that when there is water in between the tire and the road, that the water can be ejected outwards, and that there's still contact between the tire and the road. Now, braking force. It may come up. I'm not entirely sure that it will, but if Mr. Patrick's included it, then he must think it is. This is Newton's second law, also written as that. The amount of force required to stop something is a function of its momentum, and how fast it's going and how big it is. Basically, big fast things take a lot more force to slow than really slow things. I'm going to leave this here. If this is needed for foundation, then I'm going to come back and do another video. Yeah, I'm going to ignore that. I don't think that's true. If needs be, I'll do another video. This is probably important. The greater the speed of the vehicle, the greater the braking force. Now you know what to do. Get those pause buttons ready. Pause. Pause. Yep, press that pause. Answer that question. What do we call cat's feet? Pause. And here are your answers. Game. Cat's feet when the answers come up so you can see what they are. Thank the Lord that's over and done with. Okay. Well, I can't say it's as interesting as a real lesson, but you have all the information you need. Any questions, come ask us. You can drop a comment, but I have no idea how to find out what they are, or what they say, or how to read them. So probably don't do that. Just come and have a chat with us or email. Thanks for listening.